Hello, I'm Marco Flagg of Desert Star Systems, and this is a sort of a rough and ready tutorial about how to process a potentially sparse data set that a CTAG pop-up tag may have returned to you. Now, this tutorial, don't look for anything fancy here. The emphasis is not on it looking nice, just being informative. All right. Let's start with a question as to, well, why would you ever have a sparse data set from a CTAG, and doesn't that mean that there's something wrong with the tag? No, not at all. It just depends on the risk associated with your tagging mission. When we look at a CTAG here, and here you see one of them, this is actually a CTAG lot. You see a small float body, and then importantly, you see here a solar panel. And so after the tag pops off from the animal, the tag has to float to the surface, and then driven by solar power, it will transmit. The average transmission time for CTAG devices is about 5 months, and the most observed, I believe, so far is about 3 years, so quite a long time. For the smaller tags, what we call our CTAG SAM tags, which stands for Stock Assessment and Mortality, which include the lot, the geo, and the 3D right now in that family. They mostly transmit daily summaries, and you have most of your data after a month or so. So 5 months transmission time is plenty. But what can happen is, imagine a fish is close to the shore and tag pops off and it immediately washes up on a beach. Now the antenna wouldn't be pointing up anymore as it should, but down in the sand. Maybe it's obscured by some debris, whatever, and maybe now it really has a hard time transmitting. On the upside, it is solar powered, so as a situation improves, then it might suddenly start transmitting again. And we actually had an interesting case down in Antarctica where a tag surfaced, but fairly soon got stuck in the ice. And now came this Antarctic winter. And then come next spring and the ice melts and the tag was transmitting again. So hope springs eternal with solar power tags. But for now, we will look at a tag that was on a whale shark and look in the description of this YouTube video for citation and where you can get these data sets potentially, so you can follow through with it or follow us here. So it was on a whale shark tagged March 6, 2019 for a 100-day mission scheduled to pop up on June 14th, 2019. And in fact, starting July 1st, some messages were received, but not too many. And so now I'm going to show you how you can figure out what may have happened here, what the fish did, and so on. So let me get out of this picture mode. I'll close that down. I now do want to point you to a published paper by Klimley, 2017, in Animal Biotelemetry that you should read. It's called The Value of Using Measurements of Geomagnetic Field in addition to irradiance and sea surface temperature to estimate geolocations of aquatic animals. How is that of any relevance here? Actually, it's of great relevance, and it helps a lot with a sparse data set. Because as a tag is transmitting, say for a given day, magnetic field intensity value, an observed value, let's say 38,430 nanotesla here, and you combine that with the tag's observed noontime, those two parameters provide a geoposition fix. So unlike tags that don't have a magnetometer, where you have to rely on many measurements, typically of irradiance and sea surface temperature, This magnetometer gives you a much more robust situation, and it allows you, even when just a single data packet gets across, to actually resolve a position for the day. And I will show you how you can check if that position might be reliable or might not be reliable, and you have to do some interpolation. All right. That said, let's move on to give you an idea as to what the basic data is. And hang on, I want to look at my recorder here to make sure it's actually still recording, and it is still recording. So I'll get that down here again. What is the basic data that the tag is transmitting? And I put, by the way, all my data here into, combined it in a spreadsheet. That makes it convenient. I won't go over how it got there. That's a subject for a different tutorial. Otherwise, this one really gets way too long. But let's start with the raw Argos log here. So that's what you get from the satellite. When you see something in blue, that meant I did some decoding there. There's a formula behind it. You know, I can click on one. And here you see that formula here. You know, so anyway, I don't want to modify that formula here right now. But I just want to show you the sort of data that comes in from Argos. Very important is the message date when the transmission actually happened. And then, of course, if latitude and longitude is available, you get that here. And frequency and some other things, location, quality, whatnot. But then we go into the sensor data itself, and later on you will see some decoding of that. So this is our sensor data here. Just if you're curious about it, how does that all work? Well, the first byte, sensor number 1 for Desert Star, is always a packet type. It identifies what follows it, and then the second byte is the tag status, which is what I actually decoded here. So here was in shipping mode. So our first question is, why may we have had sparse reporting? And that is important to understand. And so let's take a look what our Argos log tells us here. We see the first activity data received by the Argos constellation on February 6, 2019, and there was a good number of them received for the day. That's 24 packets I can see here. And I can also tell where that was. 36.6 degree latitude, 121.7 west longitude. That's actually Desert Star's location, so that was our quality control check. And we got 26 messages for the day, and that is fine. It wouldn't have been a complete day. Yeah, this is actually, as you can see, within 1613 UTC to 1913. So it's just 3 hours. So that tag really worked well. And then the customer, later on, we shipped the tag, and now on March 5th and 6th, we see some more packets, and the tag is still in shipping mode. Let's see where it was at the time. 21.7 degrees north and 105.5 degrees west. So this is in Mexico, and this would have been the pre-tagging test by the customer. And the researcher did just the right thing. You always want to do that, you want to know, like, all right, just before I put the tag on a fish, was it working well? So if I do get little data thereafter, at least I can say, well, when I put it on the fish, it certainly was working. There wasn't a problem with it. Of course, here, notice it's in shipping mode. You have to use certain light signals. That's, again, another tutorial, and to get it into on fish mode. All right, we're now moving on. We're now on March 6th and March 7th, and we are seeing the first on fish locations. So I wasn't there for the tagging myself, but I understand that the tagging happened on March 7th, so we can't quite tell whether these messages would have been, maybe when the tag was still on the boat in the sun, which is a good idea, or whether it was actually some messages while it was already on the fish. We don't know that. Then we have a long gap, and then finally on July 1st, 2019, we again hear from the tag. It's now saying, oh, I'm in reporting mode now. So the status byte is always the current status of each message, no matter what message type it is. That starts on July 1st. When we look in the tag configuration here, which is what the researcher filled out, they requested 100 days. After 100 days, the tag should go to trigger its release mechanism, go into reporting mode, and that is, per my calculations, on June 14th, 2019. So the first time we hear from the tag is actually quite a bit later. Okay, so why didn't we hear from it on June 14th? Why only on July 1st? Does that mean the tag release failed or something like that? Again, not necessarily, right? It could be that the tag didn't have much opportunity to transmit. Okay, and so there we see, now you know why I'm saying this is sparse data set. This is literally all the data, all these data packets here from number 58 to 78. I guess that's 21 packets. That's all we received. Last one was received on October 6th, and right now it's October 8th. So 2 days ago. A good chance we'll hear more from the tag and learn more about it. We do have a position report here, which turns out to be quite a ways inland in Mexico. This is an Argos position. It requires that a satellite receive at least four messages in one satellite path. You can see that this is between 5:17 p.m. and 5:20 p.m. on the 1st of August. It met that requirement. It's called priming the pipeline in Argos speech, but that first position may not be accurate. This one is way inland in Mexico, so I would be suspicious about that. All right, so far this was just a review of our raw Argos data, and you can see that I relied quite heavily, I should say, on the decoded tag status here. Again, we're still on the question, why is it sparse? And what can we learn about what the fish did, what may have happened? And so therefore, I'm now going to go to another type of report, which is really one of the two data products. We have daily summaries and engineering packets. And daily summaries is really a summary, literally, of what happened on a given day, versus engineering packets is what's happening right now. And we'll go into that a little bit as well. But let's move on to our daily summaries. And first thing that I want to point out here is, again, we are looking at our decoded stuff here. And I want to point out this thing called checksum. So checksum can be true or false. So the checksum is actually the last byte of any Desert Star tag transmission, like here 181 and here 144. And there's a fairly basic computation that's run. I don't need to go into the detail of that one here right now. That is used to determine if a packet has some data corruption in it. Now, how common is data corruption? Well, when we test the tag here on the roof at Desert Star, we get about 80% good or true and 20% bad. There's a CLS document, quite an old one, that says look for about 2/3 good and 1/3 bad. But it does depend on ocean conditions. When you have rough seas, then then a tag will just, it's very streamlined. So you also want to submerge, and waves obscure the horizon if it's in the trough of a wave. So then you get bad ones. And so when it's a little bit rough seas, then I tend to call it 50-50 is about normal. Here, we're actually getting more bad ones. No, that's not true. Well, we're getting about the same false and true ones, although, no, I guess overall it's about 50-50. All right, so that's not really, that's fairly reasonable if the tag was in the ocean here, all right? Okay, so that is the first one here, but again, remember our question was, why so few packets over such a long reporting period, from July to October, when in a single day, when the researcher was testing it and we were testing it at Desert Star, we would have gotten more packets than in all these months. And the clue to this is in a graph that I put in, except for I can't find it. Oh, because it's not in the daily summaries. It's in my process geopositions. Okay, before I go into what process geopositions means, let's look at temperature values from the daily summaries that have been returned. Now, where you have the points, that's of course where you actually have a sample point here. And in between is just a line connecting your dots here. What we have is blue, is the maximum temperature. You'd think it would be red, but yeah, it is what it is. Average temperature is the red one, and the gray one here is our minimum temperature, always as observed in a given day. So if you have a tag on a fish and the fish dives, then you would expect the minimum temperature to go down. For example, if the average is closer to the maximum than the minimum, that probably means the fish spent more time near the surface than it did at depth. Remember, this CTAG Geo that we are looking at here actually only has 3 sensors that sense the environment. One is the magnetometer, the other one is temperature, and the third one is the light intensity. All right. So here we are seeing that the maximum temperature, which I'm going to concentrate on March 7th, it was 28 degrees. Okay, well, I guess that can happen. Here we are now on March 29th. We are 24.15 degrees. May 13th at 25.2. Then June 2nd, 23.4. June 7th, 25. And these are all reasonable water temperatures. And that's now June 7th, I guess we're here. Yeah. Now, tag was supposed to pop up on June 14th, and so far the first daily summary, we have those for June 24th. I should explain here that the tag will send its daily summaries in an endless loop. It just starts from the beginning of the mission, and then it goes until the day that is currently, and that includes the post pop-up period. So it'll still collect daily summaries each day. As it comes to the end, it goes back to the beginning, and it does it over and over and over again. So next time we hear from the tag, we probably have some other data point popping up here if it's a daily summary, which, by the way, are 90% of the messages. So 9 out of every 10 are daily summaries. 1 out of every 10 is the engineering packet. That's how we programmed it. But look what happened here on June 24th, which would be 10 days after the June 14th pop-up date. We are at a temperature of 34.8 degrees Celsius is the maximum temperature. Is that an outlier? Could that be wrong? No. Thereafter, the next data point we have, although quite a bit later, is on September 10th. And again, a similarly high temperature. And then September 19th, we are actually at 40.8 degrees Celsius. all these 3 points mean that the tag was certainly no longer in the water. It was now in the air, and it can heat up in the sun. And because it's black housing, if it's just laying out somewhere on a beach, for example, you can see these temperatures that go to 40 degrees, even all the way up to the 50 degrees Celsius. Just like leaving something on the dashboard in your car on a sunny day, and it can just get smoking hot. So that's what we have going on here. The significant thing for us in our discussion right now is that we already see that on June 24th. So on June 24th, the tag was certainly already up on land. It popped up 10 days before. On June 7th, it should have been on the fish, and it shows indeed that it was likely on the fish. We do see temperature 25 degrees Celsius that would be consistent with the area where the whale shark might be. And we do see drops to a minimum temperature 19.8. So that 5 degrees Celsius difference certainly means the fish was diving, because it wouldn't get that cold at the surfaces. If the surface is at 25 degrees for the day, it's a fairly substantial change. And it gets to be more down here and here. Okay, so what we know by now is that the tag had at the most 10 days to report. My sense is, based on the sparsity of reporting, that it probably washed up on a beach very soon. It was flat on the sand, and then couldn't transmit much anymore. You can play devil's advocate and say, whoa, wait a minute, maybe it just isn't transmitting much, period, for whatever reason. Like maybe its solar panel got compromised or fouled. Do we have anything we can tell about that? And the answer actually is yes. And I go to the engineering packets now. Engineering packets represent the current state at the moment of transmission for the tag. They actually have an important function in that these CTAG SAM tags don't use UTC time. You don't have to hook them up to a computer. They simply report mission elapsed time, or MET. And in the engineering packets, it tells you right now my MET, expressed here in days, for example, is 13.78 days. And then if you go back, hang on, let me do that here, to an earlier column. So 13.78 days was received on March 6th, 2019 at 16:08. If you subtract 13 days, you actually come to 2019 at 21:27. That's when it was last time sort of activated. That was for a test. Here you actually see the origin time for the deployment was March 6, 2019, 17:04. Okay, we were at the question though is, did this tag really transmit a lot? And yeah, the answer is yes. Because if I look here at the Argos transmission number, like how many times it has transmitted, that just kind of counts up. See that here. We're now on in February 20th, we're 685. It gets reset to 0, by the way, when you put a tag in on-fish mode. And now we are at day 176, which also happens to be August 30th. So well after it had arrived on land, and it actually had transmitted 10,020 times already. So the transmit performance actually is, pretty good. And we should have seen more messages. Why didn't we see more messages? Well, the simple answer almost certainly is, well, because this tag is flat down on the sand somewhere. The antenna isn't pointing up to the sky. Who knows what obstructions are around it? And there's actually signs that there's a lot of obstructions around it. We'll go into that in a little bit. And so that is why we are seeing a sparse data set. It's just on the sand somewhere. Okay, well, what's next? I think What we next want to look at is first give you a basic understanding of how process geopositions are actually derived, but only very basic. Again, it's for another tutorial to go into that in detail, but essentially it's done by a utility that we call ctrack. I'll briefly call it up, just to make it a little bit more interesting. I have two versions of it here. I'm going to call up this one here. Oh, there it is. And yeah, there's this little map. I can now load a log file, open the ctag log, see what I have. This wasn't really part of my planned demo here, so I hope this works. I'll find where I have this. Oh, that's the wrong version of ctrack. Turns out I have to use one with a legacy log that accepts legacy data. That has to do with how this particular data was recovered. So let me go to old version of ctrack right here, version 2.000. File, open ctag log. If I'm right, it was this one here. Let's see. Yeah, there's a bunch of, see that? I called them in, got the ctag log, and it accepted it. And I go to field strength map. Okay, I hit the low processing fish here. Tells me there's 10 daily packets. Do you see these dots popping up? Those are the resolved position. You can already say that some of them, what's this here in Utah? Not too likely, and this one is way up north. Not too likely, but some of them are right in the tagging area and here along the US-Mexican border in San Diego. We'll look at that a little bit closer for later on, but that's essentially how you get your positions with this utility called ctrack. Again, time for another video to explain that in greater detail here. Let me close that. Here, let me see if my video is still running. Yeah, we're at 27 minutes now. Okay, I hope I can get you out of here in less than an hour. And now, yes, so that's how we get our average magnetic field strength from the daily summary and the noon time. Noon time relates to longitude, magnetic field strength relates to latitude. Again, read this paper, then you will understand it. So it's very, very important that you read that. Turns out that your noontime estimate, like 1915 UTC for a given day here, let me see if I can get that, on June 24th, 2019, the observed noontime was 1950 UTC, and that translates to longitude. And I know that's reliable because it also observed a day length of 14 hours and 20 minutes. That would have gone from before sunrise to after sunset. And that almost certainly means that this latitude indication is reliable. Why is that? Because the tag uses its solar panel to measure dawn and dusk, and typically if you're at the surface, that would be measured about a half hour in mid-latitudes, half hour before sunrise for dawn, when the light is at about a level of 4 lux. Maybe you can read like the large print on the newspaper at that point, the headlines and such, right? And then at dusk, it will happen again, and the noontime is simply the halfway point between dawn and dusk. And, it can't be wrong much because, well, if it were wrong much, that would imply that either the dawn or the dusk measurement would have had to happen at night when there is no light. And so that just can't happen unless, the fish is maybe hanging out where there's artificial lights, which might happen with some species where there's human activity. Not too likely to happen with a whale shark. And we make sure that the sensitivity threshold at 4 lux is above the level of moonlight, so moonlight ain't gonna trigger it. All right, so I can rely, for example, on this noontime measurement and to give me my my longitude, and then for latitude, the magnetic field strength. I do have to be a little bit careful about that. That can have errors primarily due to a fish hanging out in the area of crustal magnetic anomalies. And again, I refer you to the Klimley paper for that. Those are like magnetic rocks close to the surface, and they mess up the main Earth magnetic field, which originates in the outer core of the Earth. It's a big dynamo effect with molten metal moving around. That Earth magnetic field is very, very smooth, and so you can get like very, very nice indication as to where you are. Look at that. Here on my Google Earth, I called it up. 42,000 nanotesla is here. 49,000 is here. And I'll already go to like way up here. These are my process positions, by the way. On June 2nd, 2019, we get a fix that, let me see if that had an apparently good longitude. June 2nd here. Yeah, it's one of my greens. The day was 11 hours and 44 minutes long. I decided that I could sort of rely mostly, it's in June, 11 hours and 44 actually isn't that the best measurement. There would have been less than the time from sunrise to sunset at that period of time. But it won't be off by way too much. And so I decided to just use that. And going back here, but you can see that the measurement of about, 54, 53, 52,000 nanotesla I get. Let me see if I have that correct. It says 51,040, so I'm not quite sure if my magnetic model here, which is from University of San Diego, if that is really all that accurate, but it gives you at least a general idea. But notice again, if I see a greater value, 55, 54, 53, that tells me pretty well where my latitude should be. But if we're now in an area of a crustal magnetic anomaly, we have to be aware of that. Then you can get an error here. And seamounts oftentimes have magnetite in the rock, and then you can get this latitude error. So you have to be aware of that error potential. Again, referring to the Klimley paper for more education on that subject. All right, so that gives us an idea how positions are generated from the noontime for longitude and average magnetic field strength for latitude. I marked these green, red, and yellow because what I did is sometimes I said, something just isn't quite right. The red ones here are ones where I replaced the observed magnetic field intensity with a value that I found more reasonable. Here it says MAG from 6/24/2019. I found this to be more reasonable. Why not 910 and 919? Let's take a look at what we actually got for these days. 910 and 919. Here they are. Okay, that's 910 and 919. This actually tells us a very interesting story as well. Notice this, 62,060 nanotesla on September 10th and then September 19th, 9 days later. This is an independent measurement, but it got us almost the same amount value, even though temperature was a little bit different. Temperature can cause some error in your readings. But 62,000 nanotesla, where is that? Where is that? Where would I have to go? I have to go here in the Arctic. Oh, geez. Now here at the magnetic pole, we have the strongest Earth field. And it's not 62,000 nanotesla. That's impossible. So I know that reading was incorrect. What does that tell me actually? Well, what that means is that this tag right now, remember, it's on the beach. We know that from the high temperatures. It's also near a man-made disturbance in all likelihood, because it's such a strong disturbance. It could be a highly magnetic rock. It's not very likely. More likely up against some metal pipe, metal object of some sort on the beach. And because it's a very consistent measurement over a period of 9 days, 62060 and 62010, between 910 and 919, means that tag didn't move much. Didn't move much at all. All right. Again, confirms our idea here, that as to what happened and why our data set is so sparse. Okay, but enough about sparse data sets. So now we have to deal with it. How do we do that? One trick that I do is, again, I do my sanity check. All right, do I have a good day length? Can I trust my noontime observation? And I just look at the length of the day. I can certainly trust this one. It was 1950, 14 hours day long. This is kind of a shortish day, but noontime is pretty similar to 1950. Here we have a noontime of 1912, another day. This is in March 29th, time of the spring equinox about, and 11 hours and 28 minutes isn't a bad observed day length. By the way, why would a day length on an animal be sometimes observed short? Well, if the animal goes very deep, then that happens, right? So they have less light, and then you trigger the threshold earlier. So that can happen, right? So, okay, I called these green. I believe the roughly, at least, not quite, I don't think we're really up in Oregon, right? So I'm skeptical about that. But anyway, I plotted it at least directly from the tag provided noontime and average magnetic field strength. Same for these and same for these. And then in some cases here, notice how the day length for these three is very short. Therefore, the noontime was essentially garbage if we look that up in the daily summaries. And so I took the noontime from the closest date, 4/20/2019. That's not even on here. You go like, well, where did you get that one from? Well, let's go back to our daily summaries. And here you see 4/20/2019. But it's got a false checksum, means there are some errors in the data packet, but yeah, that doesn't mean that all your data is bad. It's just some of them may be bad, maybe just a single byte somewhere. And this looks like a reasonable noontime to me. I don't think that's corrupted. 1910, So that was the closest time available to reliable time to 512, about 20 days away. So I replaced the observed noontime with one taken from another data packet. And so there you see that again, yellow ones, noontime is replaced, red ones, magnetic field is replaced, and green ones are sort of my anchor points. Those are the ones that I really rely on, and then the rest I'd be a bit more careful about. So what do we learn? What did the fish do? So it was tagged somewhere around here, don't have a very good position here along the central Mexican Pacific coast. And then we have these three positions right here. Don't think it moved much between March and May. Of course, it could have done an excursion and then come back, and we'll have to wait some more, see if we get some more data, and that'll help us. And then we start seeing positions that are closer to up here, June 24th. Okay. So it seemed to have gone north. I would count on that, although I would want to see more data coming in, hopefully, from this tag. And then here, 919, we were already, now on the beach somewhere here. Remember, we actually replaced the magnetic field intensity because it would have placed up in the Arctic with a more reasonable value we found at an earlier date on 6/24, which is actually 10 days after it would have released, So anyway, so that's what we got here. So really what I can tell is the temperature experience this animal had, and that it hung around for a while and then it went up north here. Admittedly, it's not a whole lot, but it's better than nothing. And the game of tagging is, it's a game of chance. Whale sharks can hang around close to the coast. Yeah, if it comes up right on the coast, then you can have a pretty poor track. But at least you're still getting something here out of it, and then I always say that you should go sort of for minimum sample size of 10 animals to evaluate how your experiment might work out. So then generally you will find that some did very good. You get very dense data sets, and then other ones are sparse. Of course, if you have a fish that tends to just go in the open ocean and stay there, then that's an easy one, and you will generally get some pretty good data on that. I think that really covers most of what I wanted to show you. We went over daily summaries, a little bit over engineering packets, the raw Argos log, how this all works, this translation with CTRAC, the fundamentals with the Glimley paper. And I hope that this will give you a start with your tags. Give it a try. Let us know if you run into some trouble here. And yes, I hope this was a useful tutorial. And with that, I'll call it a day. Best of luck.